Okay, I think I'm recording now, and I'm going to go ahead and try to get started. We have almost 20 people here, which is, I think, what my class roster says for this. You guys are all here, obviously, for Math 350. Can everybody hear me okay? Does everybody give me a little thumbs up? You got some volume coming through on your end, I hope. That's good to see. Um, and can you see behind me here? I've got a couple of whiteboards that I scraped up out of the basement of my parents' house that I'm going to try to use. I know a lot of instructors like to write on an iPad and kind of project an iPad onto a screen. I tend to be a little bit too antsy for that. I don't sit still very well. I like to get up and move around. And so I'll probably try and use this whiteboard that's behind me here. So anyway, welcome to Math 350. I'm glad you guys are all here, and I'm looking forward to the semester very much. The last time I taught Math 350, I've taught it 7 or 8 times now. The last time I taught it was right in the middle of COVID. It was the entire semester from start to finish was completely online. And I was still not very good with Zoom and still learning my way around the technology and everything. I was going back and reviewing that last time I taught the course and kind of looking at my resources and stuff and said, oh yeah, I didn't have much of a good idea how to do anything back then. I've gotten a little bit better at it now. And we are not going to be going start to finish in Zoom. If you've watched my syllabus video, which I think most of you probably have, what you know is that for the first 2 weeks, I am out of town. My parents both had surgeries late in 2024. One of them had a hip replacement. The other one had a knee replacement, and they're both kind of hobbling around a fair amount. And the doctor said it would be really great if, they had somebody who could help them, kind of through this first few weeks of their recovery. And so I'm actually at my parents' house, which is in Nebraska. So I don't know if you've ever been in a conversation with anybody from the state of Nebraska, but if you take the United States map and point right in the center of it, that's where I am. And it's about 15 degrees outside, and the wind is blowing at about 20 miles an hour, and it's freezing over here. But I'm going to be here for a couple weeks. And so today and Thursday, and then also next week on Tuesday and Thursday, we're going to meet just like we are right now in Zoom. And so if you're having any issues with either seeing anything on this board or hearing my voice or anything like that, be sure to let me know. I do have a chat function open on this Zoom, so you can type into that if you wish. Or you are also welcome to unmute yourself at any time if you have a question about something. Just get my attention, whatever is the easiest and best way for you to do that. And I'll try to address that. Also, for these first 2 weeks, obviously all of my office hours will also be in Zoom only. Once we get back to the 3rd week of the semester, I will be having my office hours both in person and in Zoom simultaneously. And it'll be your choice as to how you want to come to office hours. There's a big study space right outside of my office in the basement of McCarthy Hall. So it's a really easy way to just kind of hang out and get some work done and have close access to me. Anyway, I'll try not to repeat too much of what was already covered in that syllabus video. Did you guys all get a chance to watch that, by the way? Everybody kind of just go through. I made that a week and a half or so ago, and just wanted you guys to just check it out. If you're kind of just wondering how the class is going to work, you could certainly tune in and take a look at that. And also, my next question is, does everybody have a copy of this book? This is the textbook we're going to use. The front cover of it is pretty standard because there's only really one edition of this book. If there's anybody out there who does not have this book, if you could send me a note, you could send me an email. That might be the best way. I could send over some of the first pages of the book so you can get started. I don't want anybody having to delay their work just because they don't have the book yet. So I've got a copy here. Once I get back to Fullerton, I'll have it in my office and you can borrow it anytime you happen to stop by. But yeah, this is what it looks like. It has not been reprinted with new editions very often, and that's why I was a little concerned maybe if people would have trouble getting the book. So everybody's seems like I'm not seeing too many people unhappy about it so far. So hopefully you have the book. It's a very good book. It's thin, but in a way that's a good thing because it means that the book doesn't go off on a lot of long tangents and talk about stuff that's not really pertinent to Math 350. So I think that that's actually a good thing for us. And hopefully that'll help make the class go smoothly. We could really know exactly what we need to focus in on. So just so in case you're wondering about the book, we are going to cover pretty much up to the first 6 chapters of this book. The first chapter is just a review chapter about basics on proofs and sets and functions. And I am going to spend probably a good chunk of time today and maybe even a little bit on Thursday in that first chapter, chapter 1, doing a bit of a review about sets and functions. This is like super important. Like if you ask me what's the definition of math, I'd probably say something like it's the study of functions. Almost any class, whether it's analysis or algebra or geometry, there's always functions running in the background of everything we do, right? So in that sense, I think it's worth spending a class or two just kind of reviewing the basics of sets and functions just to kind of get up to speed with that. But by next week, I hope to be moving into chapter 2, and we'll cover chapters 2 through 6 as the core of this class. When you think about calculus, this is advanced calculus after all, you're probably thinking about things like derivatives and integrals and continuous functions and stuff of that nature. And of course, all of that is going to be part of the class. But the surprising thing, maybe the surprising thing to you, is that we're not really going to do derivatives and integrals until like the last third of the semester. That's because there's so much buildup of the fundamentals that we have to do here. We have to understand like how the real number line works and what it means to talk about limits in the context of those real numbers. And so stuff like that will take us a fair bit of time. And we're going to be, I think I mentioned this in my syllabus video, we're going to be doing this from a very precise perspective. Like we're going to try very hard to be rigorous in everything we write down. So this is not a class where you can just kind of wave your hands or you can just kind of vaguely write down something that's a little bit sloppy. It really needs to be quite polished. I'm even going to recommend that for many of you, as was true for me when I learned the class, it was a good idea to actually draft my solutions to the problems I was submitting for homework and then go back and actually write them up in a final form, rather than to just sit down and think that I'm going to write up a final version in my very first attempt, because it's hard to get it all right. You got to dot all those I's and cross all those T's. So just something to keep in mind. We have to step pretty carefully around this material. It's just the nature of the subject matter. And I'll be quick to take a look at your work and let you know if I think that you're getting things up to par or whether we need to work a little bit more on it. I'm going to try, especially early in the semester, to give you some feedback about that. Any questions so far? Everybody so far so good? You can all hear me and see me okay, I hope. Okay, great. Yeah, you can use a thumbs up. You can use your chat function or your microphone if you have anything you want to get my attention on. I guess the only other thing I'll say for now is, again, for these first 2 weeks, if you're able to turn on your webcam, that's great. I understand it's not always possible, but it's great if you can. And then the other thing is homework. There is an assignment due this Friday, which is actually only 3 days from now, at midnight. So we're going to start right into it here. This first assignment is mostly about sets and functions, just reviewing material that I hope that you've seen in another class. Math 280 would be the obvious place that you would have seen it. It's not really going to feel this week like we're doing calculus at all. This is more, chapter 1 is really more about the background behind the calculus that we're eventually going to study. So that first homework assignment is going to be of that nature as well. So feel free to jump in on those homework assignments as soon as you can, especially the one that's due this Friday. And if you've got questions, please don't hesitate to stop by my Zoom office hours. I have hours later today. And I also have them on Thursday and also on Friday, a couple of times on Friday before we actually have to submit the homework. So you'll have plenty of opportunities to talk to me about it. But yeah, it'd be good to try to get started as soon as you can. Okay, if there's no other questions so far, I'm going to take a stab at some notes here on the board behind me. I am recording this session, so if you miss anything or you want to watch it later to make sure that you've got everything down, you'll be able to do that. I'll be putting this up as a YouTube link. I have a YouTube channel, and I'll just make this into one of my files on YouTube, and I'll post it in Canvas probably by tonight. So I usually try to do it the same day as the class. Okay. So with that in mind, I guess I'll just quickly start off with, maybe I'll ask you guys a question. When you think of calculus, if somebody asks you, what is calculus? How might you answer that question? Like, what kind of things come to mind? You can use your chat or your microphone to throw out ideas. There's really no right or wrong answers here. I'm just kind of curious.
The study of change.
Okay, the study of the rate of change. That's a good idea. In the chat, I see limits. In a lot of ways, limits would be the underlying concept, right? A derivative, for example, which you think of with calculus, is really defined as a limit. And integrals are also limits. So many of the things that we study in infinite series are also defined as limits. So there's so many things that are really best explained in terms of limits. So if I was to ask, what is calculus? I'm going to go ahead and start writing on this board here, and I hope you guys will let me know if you're having any trouble seeing anything that I'm putting up here. But what is calculus? I would probably answer by saying it is the study of limits. And somebody said rate of change, the study of the rate of change. And that's certainly an example of that, right? That's a great example of that. But limits come up in so many places, right? So I've already kind of alluded to this. We can study limits to, or if we use limits, we can define what the idea of a derivative is, right? We also can talk about integrals. Integrals are also defined by using limits. Infinite series, that was another one that I just mentioned. So these are all good examples of things that are defined by using limits. So at some point, right, at some point, limits are going to become the primary thing that we spend our time talking about. And really, chapter 3, when we get to chapter 3, it's all about limits. And then in chapter 4, we'll talk about limits of functions, specifically that we're going to be addressing specifically continuous functions is what chapter 4 will mainly be about. And that will pave the way for derivatives and integrals, which, as I said, we're not really going to get to until nearly the last part of the semester. Okay, so you've all seen these ideas before, I'm quite sure. The point in Math 350 is going to be to make them as precise as possible, right? To do everything from a fully rigorous perspective. And so behind all of these things, so a limit, I'll just put this here, a limit can be expressed in terms of functions. So functions are behind everything in math, as I kind of alluded to earlier. So you might be taking the limit of a function. In the case of a derivative, that would be a difference quotient. In the case of an infinite series, that would be a function defined on the natural numbers that is the limit of sort of the partial sums of a sequence, A1, A2, A3, and so on. So there's always functions kind of roaming around behind the scenes on these things. And so to talk about functions, you have to have inputs and outputs, and those inputs and outputs belong to sets. There has to be the concept of sets behind the scenes here. So before we get into functions in more detail, I'm really going to talk for a little bit of time here about sets. And this is really covered in section 1.2 of the book. And I'm just reviewing, right? This is stuff that you would have hopefully seen before, but I just want to start a little bit slow here and make sure that we're all on the same page. So I'm going to put down a definition here of what a set is. So a set is a collection. It is a collection of objects. Okay, these are sometimes called elements. So it's a collection of objects called elements. Is everybody still able to read this okay? Hopefully my handwriting is decent enough. I'm kind of writing sideways here. It's a lot easier for me in a regular classroom, but I'm doing my best to write with good penmanship here. But yeah, a set is really the starting point for any conversation about anything in math, because functions rely on sets. You have to have a domain and a codomain for your function, and those are sets after all. So with that in mind, I'm just gonna click this thing off, there we go. With that in mind, I want to also talk about the cardinality. Okay, so I'll just put this with the same definition here. The number of elements in the set let's call the set capital A. I will usually use capital A, capital B, capital X, capital Y, whatever, but a set is usually denoted with capital letters. The number of elements in the set A is denoted with these sort of absolute value bars around the set. So we put like the set A with bars around it. It's not really literally an absolute value bar, but we can use that notation. And this is called the cardinality. So this is called the cardinality. The cardinality of capital A. It's just the number of elements in the set, which of course could be 0, right? Or it also could be infinity. It could be any value that you might think of. So for example, there's the empty set, which is just, again, I just want to make sure we all have the same notation in mind. The empty set is just written this way. We put these little squiggly braces for the notation of a set. And if there's nothing inside of it, that's the empty set, and it has a cardinality of 0, right? We could also talk about, there's some other sets that we're going to be using all semester long, so I might as well use them as my examples now. The natural numbers, this is kind of written with a math boldface N, and the natural numbers consist of just the positive integers. 1, 2, 3, 4, and so on, ... like so, right? That's the natural numbers. If we want to include the negative integers, we would use a Z for this. This is like a math font of a Z. And this would include negative numbers as well. So ... -2, -1, 0, 1, 2, 3, and so on. So that's the set of integers. Of course, that has an infinite cardinality. Obviously, that's an infinite set. If we want to go even larger than the integers, we could talk about the rational numbers. I'm going to use a Q for this. So the Q is the set of fractions. I'm going to try to write this down here on the bottom of this board here. So fractions M over N, okay, M over N, such that M is any integer. So M is an element. So I'm using this element symbol here that I'm sure you've seen before, the little sort of epsilon looking notation here. M is an integer and N is an integer, but not 0. So there's a little piece of set notation. I write Z with a backslash and then a 0. Is that readable? Sort of. Hopefully it's big enough. That's a Z with a backslash of 0. That means I'm removing 0 from that set. So the denominator of my fraction, as we all know, we can't have a 0 in the denominator of a fraction. So the N, which is in the denominator, must be non-zero, okay? So anything that can be expressed like that, a fraction of two whole numbers where the denominator is not zero, that's your rational number set, okay? It includes all of the integers, by the way, right? It includes the integers within it. And then, of course, we can go all the way to the biggest extreme that we're going to look at in this class, which is the real numbers. And the real numbers, excuse me, the real numbers here, I just have to write them as it's the set of real numbers. And we're using a math boldface R for the real numbers. Okay, so we have all of these sets here, the empty set, the natural numbers, the integers, the rationals, and the reals. And for our purposes in Math 350, those are really the only sets that we're going to have to use. Of course, there's other sets like the complex numbers, but we don't really need complex numbers to do this class. That's another class in our curriculum. So at least for our purposes, this should be more than adequate for us. Okay? Any questions so far? Nice. I'm hoping this is just review. I'm trying to take it relatively painlessly through this first part of chapter 1. A few more definitions having to do with sets. I'm going to try to come over here and see if I can write on this side of my, I got 2 pieces of plywood here that I can write on. Let me tick that up just a little bit there. Okay. Still readable, I hope. Let's come over here, and what I want to talk about here is the concept of a subset. So a set B is a subset of C, and this is usually written, well, in our book, this is written with sort of a sideways U, so B is a subset of C. But you'll also sometimes see it written with a sideways U with a line under it, and I actually like that better most of the time. So you'll usually see me writing subsets like this. B is a subset of C, like so. But our book doesn't put that line underneath of the subset symbol all of the time. But it's okay. Both of these are well understood. And this just means if every element of B is also in C. So every time there's an element in B, it should also be an element of C. And if that's the case, then we write that B is a subset of C. Okay, and so just as a quick example, I'll usually write EX anytime I want to do an example of something. So just to show you an example, obviously the empty set, which has nothing in it, right? The empty set has nothing in it. That is going to be a subset of the natural numbers, which in turn is a subset of the integers, which in turn is a subset of the rational numbers, which in turn is a subset of the real numbers. So all of those sets that we just talked about a moment ago to get some examples started are actually related to each other in this containment sense. So we can kind of measure the size of a set a little bit in that fashion, although be careful, it's maybe not quite as clear as I'm trying to imply. For example, next week we're going to learn that the integers, even though the integers are a subset of the rational numbers, the integers are basically the same size as the rational numbers. So it's kind of interesting that even though one of them is inside of another one, when the sets have infinite size, right? When the sets are infinitely big, it's actually possible for one of them to be strictly inside of the other, and yet they have the same cardinality. This word cardinality, the same number of elements. So we'll talk more about that next week. It's a little bit of a slippery concept that I don't want to get into too much right here. Questions so far? So far, so good. Okay, we have a bunch of set operations that I know that you are familiar with, but I just want to, for the record, write them down. set operations here. Things like, I know you've heard of these, we could do, first of all, we can do what's called union. Right, so we can take a union of sets. So if I wanted to take A union B, right? Let's just get the notation for this. This would be equal to the set of X, I'll call it little x, such that, whenever I want to write such that, I will either use a colon, like I did right here. So I just put a colon on this notation. You can also use a bar, a little vertical bar would also represent such that, and that's also fine. And then we're just gonna write X is an element of A, or X is an element of B, like that. And the word or is very important here, right? So with union, we're talking about or. So these are the elements in the union of A and B consist of anything that was an element of A or an element of B. It makes it a larger set actually, right? Because you're throwing in all of the elements from either of the two sets. So that's the union. What's the companion concept that goes with union? Does anybody remember, or has the winter break been too long?
Is it intersection?
There we go. That's right. Thank you. It is intersection. Let's put that one down as well. Intersection. Right. So we can talk about the intersection of two sets. Yeah. And so this is written with the upside down U between the two sets. So A intersected with B. And this is essentially the same thing. The set of X such that the only thing that's different here is that instead of X an element of A or X is an element of B, now for the intersection, we're looking at the elements that are elements of A and elements of B. So the or turns into an and. That's the only real difference there. Okay? Again, as I am keeping one eye on my chat, so if you're having any questions, be sure to use the chat or just unmute yourself and let me know. I'm going to go through a couple more of these set operations, and these are going to be important for us. I'm not just doing this to give myself entertainment this afternoon. We actually do need this stuff. I'm going to talk next about set difference. So set difference is another operation, and this can be written as A minus B. And you're not literally subtracting the sets because that doesn't really make sense. We don't know how to do that literally. But what this is that this is the set of elements X such that X is an element of A and X is not an element of B. Notice I'm putting a slash through the element symbol on this one, right? So if I put a slash through that element symbol, it just means does not belong to. So in this case, X does belong to A, but does not belong to B, right? So that's the notation for set difference. This is also sometimes written, I already used this notation once a few minutes ago, with a backslash. Right, so I took the A backslash B. That's another equally recognized notation for set difference. So you see I used that down here, didn't I? Z minus the set of 0. I took the integers and subtracted out or removed out the 0 from that. Okay, so yeah, that's sometimes it's helpful to draw little pictures of these things, like you might draw set A like this, and here's set B. Right, and then you can identify on this so-called Venn diagram, where are these set operations leaving us? So A minus B would be this section right here, right? The part that's consisting of the elements that are inside of the circle A, but outside of the circle B, right? That's the set difference. Okay, and then fourthly, one more for you here to add to the list so far. And that would be Cartesian product, which is a little bit different than the first three. Let's write it down. I'll call this one number 4, Cartesian product. Cartesian product. Okay, so let's talk about how this one works. This is written with a cross or an X between the two sets. So we have A cross B like that. And this is a set consisting of ordered pairs. So you're going to make pairs like little a, little b, and make an ordered pair out of it as if it was like a point in the xy plane. Okay, and what this is this is just the set of pairs such that little a is an element of capital A and little b is an element of capital B. Right, that is your Cartesian product of two sets. This A cross B really doesn't exist in the same universe as A does or as B does. So I can't really make any subset relationships with the Cartesian product. See, if I want to, I'll go back and just do one more quick example here. All right, if I want to, I can make a relationship between the intersection of A and B compared with, let's just say, A, as compared with the union of A and B, right? So everything that is, every X that lives in the intersection of A and B does have to live in A. And once every X that's living in A has to live in the union of A and anything else, right? So we can make that chain of subsets with no problem. But if I asked you, where does the Cartesian product fit into this chain of sets here, the answer would be really that it doesn't fit in at all. It's a different animal altogether. It doesn't even look the same. The elements consist of pairs of objects rather than just single objects. So the Cartesian product in that sense really lives in its own universe. But it's very important because Cartesian products are one way to represent a function. Right, guys? Functions have inputs and outputs. That's two things that are paired together, right? That are related to each other. So you can describe a function using this Cartesian product notation. So it's good to kind of be familiar with it. Okay, so far so good? I hope this isn't too slow. It's also just, I have to get warmed up for the semester too. I get a little bit, during the winter break, I get a little bit lazy, I guess. And it takes me a while to kind of get my mojo back up again. But I'll get there. So I'm going to try to erase this board, which is never an easy thing. Amber knows my trials with erasing boards quite well. So we're going to have that here as well, I think. My parents have relegated me to the basement of the house. So all of the heat is upstairs. So I'm down here in this cold room, and I don't know if you've ever tried to erase a board when you're in a cold room. Doesn't work very well. Actually, during COVID, I had to teach, I have a summer house out in Colorado also, where I go in the summertime. And my parents didn't want me anywhere inside that house because it's a fairly nice new place. So they sent me out to the garage. And I started off in August, you know, the start of the fall semester in the garage, and everything was fine. I did just great. But then by the time we got to about November, it was freezing out there. And I could not erase the board. It's so cold. If it's like less than 50 degrees, good luck. It's just like impossible. So I had to like haul in a space heater and blow a bunch of hot air onto the board to try to start getting it to wipe off and everything. It was a trying time. So at least now I'm not surprised when these things happen. Luckily in this room, it's not quite that cold, but yeah, it's still a little bit tough to erase sometimes. Okay, let me write down a few properties about sets. So we've written down some of these set operations, but I also want to go over, I guess I'll call these some basic laws. That, again, I'm pretty sure you're going to be pretty familiar with these. There's going to be about 7 or 8 of these to make a quick little list of, but these are just basic laws about sets. So the first one is, you know, if you take A union B, that's the same as B union A. And the same thing is true for intersections, so I'm just gonna put that one down at the same time. So if you do an intersection or a union of two sets, it doesn't matter what order you write the sets down in. This is referred to as the commutative law. So union and intersection are commutative, all right? I think everybody's probably not surprised by that. And then we can do the associative law for unions and intersections as well. So if I had three sets, A, B, and C, and I took a union of all three of them, let's say I took A union, B union, C, well, you'd have to do them kind of two at a time. And it turns out it does not matter what, how you group them, in other words. So if I want to take the union of three sets, I can do that sort of by first taking the union of the first two sets, and then viewing that as a new set, I can take its union with a third set. But if I prefer, I could just take the union of the second and third sets first, and then the union of that with the first set. Makes no difference. And same thing for intersection. So I'll just add this one directly below. Same exact idea. Essentially, this is what's called the associative law. And the thing about this, all this really says, guys, is that parentheses don't matter. When you're doing unions, exclusively unions, parentheses don't matter. Or if you're doing exclusively intersections, parentheses don't matter, right? So that's kind of nice. You don't have to be careful with it. You can just kind of write them all down. But what does often happen is that we start getting situations where we are mixing the unions and intersections together. Right? So that can sometimes happen. I'm going to put this down as number 3 here. This is going to be giving us what's called the distributive laws. So there's 2 of these as well. We can take A union the quantity B intersect C. And that turns out to be the same thing as A union B intersected with A union C. So when I mix intersections and unions together, it gets a little more complicated. As you can see here, we sort of have to take this A set and union it with both B and C individually, and then compute the intersection at the end, right? And we can do the same thing the other way around. If I took the intersection of A with the quantity of B union C, this would be the same as the quantity A intersect B union the quantity A intersect C. And this is collectively, these are known as the distributive laws. So we have the commutative laws, the associative laws, and now the distributive laws as well. This one you just have to be a little careful with, that you don't get the unions and intersections in the wrong places. A little bit of practice with that, just to be sure, wouldn't be a bad idea. And then the fourth one is also going to be a little tricky in terms of making sure you keep straight where the unions go and where the intersections go. These are the so-called De Morgan's laws for set differences. So we have, the first one is a set difference of the quantity B union C. So if I have a set A and I want to take out the union of B and C, then it turns out that that's the same thing as starting by just taking out A and just taking out B. I'm sorry, taking out B and then just taking out C, doing those separately. But then you have to switch the union to an intersection. Okay, so if I subtract a sort of the union of two sets, it's the same as doing an intersection of two other subtractions, right? And the same thing works for the intersection. So if I had the set A and I do a set difference by removing the intersection of B and C, this can be thought of as A minus B union A minus C. Okay, and so yeah, these are called the De Morgan's laws. And this sort of idea of how De Morgan's laws works, it really comes up a lot of times when you're writing proofs too, especially if there's proofs with cases. You have A or B, or sorry, B or C, something like that. You have B or C and you want to like negate that. You want to subtract it or take the negative of it. Well, you have to keep in mind that you can't just keep the union as a union. It switches to an intersection. So the or turns into an and, or an and turns into an or. Have you guys ever done a proof by contradiction? Where if I say, you know, prove that today is either Tuesday or Thursday, right? Well, by way of contradiction, you would have to assume that today is not Tuesday and today is not Thursday, right? And so your or that you're trying to prove, this union statement, turns into an assumption that looks like an intersection. So that's a reflection of De Morgan's laws, really. Okay. Are there any questions about any of these laws? Have you seen them all before? Somewhere at some stage of the game, hopefully. Yeah, we're just reviewing. I'm hoping that today is mostly just review of some basic set theory here. You know, I should mention, of course, that all 8 of these statements technically have to be proven. And here we are in Math 350. We've almost made it through 45 minutes and I haven't done a proof yet. How is that possible? This class is all about proving things and we will be doing many, many of them, right, throughout the semester. So yeah, technically we would need to prove all of these things. Just as a general strategy, let me just add this here as a strategy for proofs with sets. And you will no doubt have done this before, but I just, again, want to be very clear, which is that if you want to prove, these are all equal signs, right? All of these are, just circle them here. These are all equal signs on these 8 statements. To prove equality of sets, we would need to prove that each one is a subset of the other. So to prove, let's say that A equals B. Let's say we want to prove that 2 sets are equal, A and B. We must show that A is a subset of B and B is a subset of A. This is typically the way this would be done, right? That's normally the way that we would try to do it. Okay, let me just erase a little bit over here. It's a little slow, but I'm getting there. Gives you guys a break anyway. Yeah, thanks for your patience with all of this too. Really appreciate it. Did some of you get to stay home today, or did you still have to come to campus anyway and deal with the parking? At home? Some of you at home, some of you at campus. Well, if you're at home, I feel good. I saved you a trip in today. Save a little gas money and a little parking. But many of you probably also still have other classes today too. So I avoided the parking completely, which was nice. Guys, you don't always have to prove that 2 sets are equal by showing subsets both ways. Let's say that I know that my 2 sets both have 27 elements in them. They both have cardinality of 27. Well, if they have the same cardinality, then you would be able to only have to prove that one of them was a subset of the other. And then by virtue of the fact that they are the same size, you would know that they're equal. So sometimes we don't have to do this. This strategy is great, but I'm not going to say that it's the end all be all of set theory proofs. You can sometimes find other ways to do these proofs. Let me just do a quick example of a proof. I'm feeling guilty. 45 minutes and I haven't done a proof yet. So let's do a proof here, maybe on this side over here, involving some basic set theory. Okay, just to kind of practice a little bit. Also, the other reason I want to do this proof, even though it's an easy proof, is just to sort of let you see how I'm writing these things up. Now, guys, I am generally the type of professor who, if you submit something and it's correct, I'm usually okay with it. It doesn't have to be my way. You don't have to write it exactly the way I write it. I'm going to write it a way that I really think is good and would be helpful. But I know that sometimes students will tell me that, oh yeah, this professor makes me write it this way, and then another professor makes me write it a different way, and it's all kind of catering to whatever the class was and who was teaching it. So I'm going to try to be flexible with it, as long as, of course, it's mathematically, logically correct, and it's communicated with enough detail that I can follow it, right? I'm generally going to be okay with anything that you might submit. So let's do this. Let's do this little proof here. Let's prove that if A is a subset of B, then A is equal to B minus the quantity of B minus A. Just to give us a little warm-up proof here, this statement is pretty easy to prove, but there's at least a little bit to it that we might have to do. Now, if we don't know how to start the proof yet, there is nothing wrong with doing a little chicken scratch and writing some notes for yourself that might be helpful in terms of just building your intuition so you understand how to do the proof. So in this case, I might start off by saying, well, I'm going to draw a little diagram of it, right? So there's nothing wrong with doing this. We have two sets, A and B, and in this case, one of them is inside of the other one. And then I can ask myself, well, does this statement look like it's true? So B is the bigger circle, and I'm going to subtract out from that B minus A. Well, B minus A is the shaded part. So let me shade that in here. I'm going to shade this in right here. This is B minus A. So it makes this little ring here. That's B minus A. And if I take B and I remove the shaded part, then what I'm left with is the inside part, which is exactly A. So this comes under the heading of great intuition, perfectly fine to draw that picture, but it's not a proof, right? It would not be written out in the kind of rigor that a Math 350 class is going to demand. So I don't mind seeing this kind of stuff, but at some point we would want to write down a polished proof of this statement. And we are proving equality of sets here, guys. And so as I just talked about a few minutes ago, the good strategy for that is to prove that each set is a subset of the other one, right? So I'm going to prove the subset this way. And I like to use these notations to kind of lay it out for myself. I'm going to give myself some space to write the proofs of both subsets here, okay? To prove the subset from left to right, what does that mean? That means everything that belongs to the set on the left needs to be belonging to the set on the right. I would like to prove that, right? So what I'm going to do here, guys, is I'm going to assume that X is an element of A, right? And my job is to prove that X also lives on the right-hand side. So what does that mean? X has to live in this set difference of the B and the B minus A. Now, if X lives in A, can you guys tell me where else does the X have to live?
B.
Yeah, it's going to live in B, isn't it? Because the assumption at the top, right, by assumption, A is a subset of B, and so that tells me that X is going to be an element of B. Anything in A is also in B, right? However, X is not an element of B minus A, right? Remember that B minus A, those are the elements that are in B, but not A. X is an element of B that is in A, right? We started off by assuming that X is in A. So therefore, X is not in the difference of B and A. But it does live in B, and so again, I'll just say by definition here, by definition, X is in B, but it is not in B minus A. So it lives in that set difference. Okay, that look all right? Okay, so that would be a reasonable write-up, by the way. It looks pretty good. Let's try and prove the containment going the reverse direction. So I'm going to start now with the second half of the proof here. I'm going to assume for the second half that X is an element of B minus the quantity B minus A. And I would like to prove that X then lives in A. And by the way, sometimes some professors and some students like to write out what it is that they're trying to show. Like, we need to show something. And you could say, well, we need to show that X is an element of A. If you like to write that down as part of your proof, nothing wrong with doing that, okay? I'm not going to do it here, but it would certainly be fine to do that. In this case, X belongs to this set difference, right? So let's just write down, what does this mean by definition? This means that X does live in B and does not live in B minus A. Okay, so that's just I know I've already erased the definition of set difference, but the set difference definition is that X lives in the first set, but does not live in the set that has been subtracted out, which in this case is B minus A. Okay, so far so good? Now what are we gonna do from there? My goal is ultimately to prove that X has to live in A. Is there anybody who has an idea? We do know that X lives in B and that it does not live in the set difference of B minus A. Can we get anywhere with that? Anybody want to try to explain that one? Yeah, Hongjun, you've got it totally right there in the chat. X is going to be in A. Let's just make sure we understand why that is, okay? The reason is that X is not in B minus A. B minus A, remember, what is that set again? That's the elements that do belong to B, but don't belong to A. And X is not in that, is not at that party, right? X is not satisfying that condition. So the fact is that the X has to be in A. You know, I actually think the way I logically think about this one almost is by way of contradiction here. What if X was not in A, right? If X is not in A, then we can write this as part of our proof, right? If X is not in A, then the fact that it was in B, right? X is in B, but not in A, that would mean that X is in B minus A, which is a contradiction. Hey, I'm getting to throw a little proof by contradiction in the middle of this. Okay, so that's kind of by way of contradiction. That if X is not in A, we get a contradiction, and thus we conclude that X must be an element of A. There we go. Okay. So far, so good with that proof? Does everybody follow it okay? Sometimes I'll put a box at the end of my proof just to make it clear that that's the end of the story and we've got the whole thing totally done. Okay. I just wanted to do that, not because it's a difficult thing to prove or anything particularly exciting, but just to kind of make a few comments about proofs, because this class is going to have a lot of them. By the way, guys, I am a pure mathematician, so I know some of you are coming to me from actuarial science and applied math and all sorts of other things. I am a very pure-minded mathematician. I can do all of my work with pencil and paper. I'm pretty theoretically minded, and I care a lot about good exposition of proofs. And so, well, it fits part and parcel of what Math 350 is all about. It's there's a lot of proofs here. So anyway, I wanted to set a good example to start off with to sort of show you how some of these proofs might work. Okay, well, so far we've been talking about sets kind of in abstract, set theory language. But of course, the sets that we are mostly going to be playing with in this class are going to be part of the real numbers, right? Because we're studying calculus where the inputs and outputs of our functions are going to be subsets of the real number line. So I just want to make sure that everybody is familiar with these notations here for sets that are part of the real number line. So I'm going to use a notation here to describe this. By the way, I'm going to talk for just a few more minutes and then we're going to take a break. This class is 2 hours long now, and I think it's just a long time to ask people to sit every day for 2 hours. So we'll always take like a 10-minute break in the middle of class, roughly in the middle. I'm not going to promise exactly when I'll do it, but I'm going to do it pretty soon here. I just want to get one more thing down and then we'll take a little 10-minute break. Okay. So the notation I want to have here is for intervals in the real numbers, because these are going to be the kind of sets that we actually have to work with in Math 350. So we have the interval from A to B, for example. Oh, so sorry, let me back up here. Let's let A and B be elements of the real numbers. So remember, we have our bold R notation that just stands for the set of all real numbers. So I'm going to let A and B be real numbers. This is the interval from A to B, but it is the closed interval. So this is the set of X where A is less than or equal to X is less than or equal to B. Okay, so that's going to be the closed interval. We can also talk about the open interval from A to B. So this would be, open parentheses on the A and the B here. This is the set of X such that A is strictly less than X, strictly less than B. All right, but then so that one's open. So we have the closed interval AB, the open interval AB, and then of course you can do open on one side and closed on the other. So we could have open on the A side and closed on the B side. This is the set of X such that A is less than X is less than or equal to B. And then we could flip that around and do the closed one on the left side and the open one on the right side. This is the set of X where A is less than or equal to X is less than B, strictly less than B. So be careful with your less thans and your less than or equal tos. These are actually very important to be clear about because the properties of these intervals changes a lot depending on whether you're using a closed interval or an open interval. The two that I put down here, they're not closed or open. They're just sort of, I guess you could call them half open or half closed. We can also throw infinity into the mix. Anytime we use an infinity here, we will always use an open parentheses on it, but this is just allowing us to say, look, the set of X such that X is greater than A, and there is no upper constraint on it. Right, X could be as large as we want. We could also go down to minus infinity, and maybe this time I'll use a closed bracket on the B here. So these would be the set of X's such that X is less than or equal to B, right? So these are just some examples of sets on the real number line, and we will very often be using them to do stuff. Right. Okay. Any questions on that? It's pretty straightforward. Okay, great. Guys, it is, oh, wow, I hit the clock exactly at 2 o'clock right now. Let's take a break for about 10 minutes. As I promised, I'll give everybody a chance to decompress for a few minutes. And at about 2:10, we're going to start up and I'm going to talk about arbitrary unions and intersections for a few minutes. But if you need to go get a drink of water or step away from the computer for a couple minutes, which is what I'm going to do, that's totally fine. And we'll see you back here in about 10 minutes. Guys, if you're out there somewhere within the sound of my voice, I'm going to start up again in about 1 more minute. So this is not a bad time to make your way back over here. Oh, that cat is so cute, Litzy. Oh my gosh. I love pets and animals, especially cats. I had a cat for quite a while.
She just, whenever she sees the iPad, she just has to be in front of it. So
She can start getting used to my voice, and she'll be excited for the math lectures in the next few weeks.
she's graduating with me.
Oh, good. I'll be sure to print an extra exam for her.
You have to accept paw prints.
Paw print answers. Okay. Sounds good to me. All right, guys, if you're anywhere out there within the sound of my voice, this would be a good time to come back over to the board here. Yeah, we have about 40 minutes left. I'm just going to keep cranking through some of this review material. Please know that I'm not planning to spend 2 hours lecturing every single class period. We will do group work activities from time to time. I'll take questions, obviously, as well. And so I hope that there'll be more give and take. And certainly once I'm back in person, it'll be even easier to make some of those things happen. So try your best. I'm trying to make this as animated as I can. I really am excited about the material, but I don't know if you can tell that from 1,500 miles away. I try my best with this stuff. You know, one of the things that I've noticed about, some of the students that really have succeeded in Math 350 in the past, and I have taught this class many times, so I've sort of got enough data now to kind of draw some conclusions, is that students that are asking lots of questions, and I don't mean like necessarily in the middle of my lecture or during class or anything, although that's certainly welcome. But I just mean in general, pondering the material sort of above and beyond just jumping through the hoops of the homework questions. So I'm going to try to give you maybe some examples of what I mean by that. So you might be asking yourself, he showed us how to take the union or the intersection of two sets. What if it was more than two sets? Could we do that? Would that make sense? What if I wanted to subtract 3 sets instead of 2 sets, or things like that? You can make up your own questions really easily with this material and ask yourself almost rhetorically these questions and play around with them a little bit. So I encourage you to do more than just kind of nodding along with my lectures all the time. But in addition to that, if there are things that come to mind that might be extensions or natural follow-up questions, I invite you to write those down, tinker with them a little bit, maybe even ask me about them. And maybe I'll know the answer, maybe I won't. But those kinds of sort of discovery-minded approaches to this material can actually be a good way to succeed, I think. And so I just want to encourage everybody to do a little bit of that. And I'll try to show you more of what I mean by that as we go along here. I just mentioned a moment ago taking unions or intersections of more than 2 sets. And so that is actually exactly what I was going to talk about right here. So it's kind of a nice segue into this. Of course, we can take any number of sets, right? So given any number of sets, let's say A1, A2, A3 and ... Let's say we go all the way up to n sets. So given sets A1 through AN, you know, we can form unions and intersections of those, right? So we can form, you know, A1 union, A2 union, ... union AN. The thing is that ... dots are sort of vulnerable to being viewed as not formal, not rigorous. Sometimes the ... we don't really know, well, what really is supposed to come next. Here it's kind of obvious that I'm talking about A1, A2, A3, A4, but it may not always be so obvious. So I'm going to give you a better notation here, which is what they would call a closed form of this union, which is I'm going to just draw a big union symbol and I'm going to write A sub I next to it. So the union of A sub I, and then I'm just going to index this union by writing I going from I equals 1 up to n. So this is just a notation, right? This is just a notation for a large union of n sets, and I'm indexing them with this little I here, okay? And of course we can do the intersection the same way. A1 intersect A2 ... up through AN. This can be written as a giant intersection. Again, I going from 1 to n. So we put the I equals 1 underneath the intersection and then the n on the top of it. And now that's just a notation for the intersection of all n of the sets. And you notice I don't have any parentheses on these expressions, and that's because we talked earlier about the associative law for unions and intersections that says that basically parentheses don't matter. We don't need to use them in these kinds of set operations. So the union of all of the sets, those are just every single X that lives in at least one of the sets, right? It lives in A1 or A2 or A3 or A4 and so on. The intersection is the opposite concept. Those are the X's that live in every set between A1 and AN, okay? Now that's probably fairly easy to keep track of mentally here. We have some finite number of sets, but you know the number of sets doesn't even have to be finite. And I want to expand this notation even a little bit better to be even a little more arbitrary. And the way I'm going to do that is I'm going to talk about something called capital I, which is a set. It is called an index set. So we might have a collection of sets that are indexed by another set, which is what I'm calling capital I here. So this is a little bit of notation. And then what I'm going to do, guys, is I'm going to assume that for each, let's call it alpha belonging to I, so each alpha, which is an element of I, that there is a set which I'm going to call A sub alpha. Okay, so I'm abstracting the notation just a little bit here. Is this all still pretty readable for everybody? Okay, good. Yeah, so far so good on that. I'm glad to hear that. So assume that we have some index set, which could be anything, right? It could be infinite, it could be finite, who knows? But there's a set associated with each element of capital I, right? So in this case, we can then form a big collection. I'm going to call it script A here. And I'm just using the book's notation for this. This is just like a script A notation. It's kind of a weird, funky looking A. But that is going to be the set of all of these sets. It is the set of all of those A sub alphas where the alpha runs through this index set capital I. Okay? Try not to get too burdened down in the notation. The capital I is really in the background here. It's not really, you know, where the action is. It's not going to be involved with the unions or the intersections or anything. It's just an index set that is sort of allowing me to list out the sets that I am putting into this collection. So this is what is called, this is an indexed collection of sets, right? That's what I'm doing here. I'm making an indexed collection of sets. How many how many sets are in the collection? Well, that's just however many elements capital I has. The size of capital I dictates how many sets are in the collection, because there's one set for each element of capital I. That's kind of the way this is being set up.
Professor?
Okay, so, sorry, question?
Yeah, what does the colon equal mean?
Oh, that just means I'm making a definition. Thank you for that question. So I'm defining the set A here to be this set of sets. And so if you see me, it's kind of a bad habit I picked up over in computer science. If they're writing code and they want to make a definition of something, they'll use like a colon equals to make that definition. So that's all we're talking about here. So this is a set of sets that we are putting into this collection that is indexed by another set that could be anything, right? So it gets a little confusing that way. Does that answer your question?
Yes, thank you.
You got it. Good question. Thank you. Okay, let me just show you a quick example of this. Let's suppose, just so we have something to play with here, let's suppose that my index set is the natural numbers. That, of course, means that I have an infinite collection of sets that I'm going to be working with here. And what I'm going to do is just make up some sets here. I'm going to define, I'm going to let A sub alpha be equal to the interval that goes from negative alpha to 1 over alpha, and it's a half open interval. So it's open on the negative alpha side, and it's closed on the 1 over alpha side. And now this alpha, let's not forget, alpha, where does alpha live? It lives in the index set, which for this example is the natural numbers. So alpha is either 1 or 2 or 3 or 4 or 5, right? It's the positive integers. So I have a set A1, I have a set A2, I have a set A3, A4, if I have all of those, right? There's infinitely many of them here. Okay. Hopefully that makes sense. I'm going to come back to this example in a minute, but I want to talk now about actually forming an arbitrary union or intersection in this sort of more abstract discussion that we're having right here, okay? So what we can do is we can form, so I'm kind of going back to what we said at the top of this board. We can form, and now instead of taking a union of just n sets, I am going to take the union over the entire collection script A, right? And this is going to be equal to the union of all of the A sub alphas, where alpha is an element of I. So here's the notation, guys. Here's the notation. I just simply write alpha an element of I underneath my union symbol, and then I have my set A sub alpha. And I can also do the same thing with intersection. I can intersect all of the sets of script A, and that's just a big giant intersection of all of the A sub alphas. So in the notation at the top of the board, I sort of wrote I equals 1 on the bottom and then n on the top. In this notation, there's nothing written on the top of the union or the intersection. Just on the bottom, underneath it, we would write, alpha, an element of I. And that just tells me, okay, I'm taking a union of all of the sets that are in the collection script A. So let's come back to our example. So in the example above, so we just have this example. Let me circle the example so it doesn't get lost in all of the other writing here. So I put a little box around my example. In that example, let's see, what would it be if I took the union where alpha is an element of capital I of the A sub alphas. So remember, I is the natural numbers. So this is just A1 union A2 union A3 union A4, and so on. I'm wondering if anybody, well, let's give everybody 30 seconds. I'm gonna be quiet for 30 seconds. I want you to think about these sets right here, these half open intervals. If I took the union of all of them, let's think about what that would give us. So the first one would be the interval from -1 to 1. The next one would be the interval from -2 to a half. The next one would be from -3 to a third, and I'm taking the union of all of those. And if it helps you, you can even draw a number line on your paper, kind of draw visually how these sets might look. Maybe I'll just squeeze that in up here. So I said -1 to 1. That's kind of open on the -1 and closed on the one side. So sometimes I'll draw these kind of casual pictures to help myself visualize stuff. And then -2 is over here, 0 is here, 2 is here. The next one is -2 to 1/2. The next one is -3 to 1/3. Anybody have an idea what the union would be? If I take the union of all of these going on forever, alpha going all the way out to infinity. So we're taking the x's that belong to at least one of these sets. So you can start shading in this interval, right? -1 to 1, that's all included. -2 to 1/2, that gets included. -3 to 1/3, all of that gets included. Look how much of the number line is being shaded in. If I was to continue this all the way to infinity, the question is, what would I end up with? I see it in the chat, actually. John is out there, and I see some idea here that we're going to have an interval from -infinity. Do you see that? See how we're shading into the left as we keep taking more and more unions? That's going to keep going forever, right? Because we're taking this union forever. It's going to go all the way to -infinity on the left. And so we're going to draw this as an interval with -infinity on the left side. But you'll also notice that we never go to the right of 1. Right? We never get any further to the right of 1. So it would be 1, including 1, right? So it's a closed bracket on that 1 because the 1, there's a closed bracket here, right? In the definition of A sub 1. So we would not be surprised to have a closed bracket there. Does this make sense? Okay, great. Yeah, so that would be the right answer. Let's do the intersection as well. So let's do the intersection of A sub alpha, where alpha is an element of I. So now I'm looking for which x's belong to all of the sets. And again, I'm open to your thoughts about that. Start drawing my picture one more time here. 0, 1, 2, -1, -2. So we start with -1 to 1 like that. That's the first set. So the intersection is already going to be contained within the first set that we draw, right? It can't be anything outside of that because the intersection are the elements that belong to every set. The first set is already limiting me to just this much of the real number line, right? The next set, yeah, it goes out to -2, not that that matters, but it gets cut off at 1/2. So that actually cuts into the right side of this interval here that we're looking at, right? And the next one's going to cut into it a little bit further because we're going to have 1/3 on the right-hand side for the third set. And what's going on the left doesn't matter because we can't ever go, we can't, the first set did not include anything to the left of -1. So it's really just, gosh, I can actually just erase this. Doesn't even matter. And what do you suppose that's going to come out to be? Oh, there's some ideas in the chat. Yeah, exactly, guys. It's going to go from -1 on the left to 0 on the right side. That's exactly right, including 0, right? Including 0, because 0 is going to be part of every one of those sets. But if you tried to take even a half step to the right of 0, or even a 1/1,000,000th of a step to the right of 0, you would eventually find one of these A sub alphas that excludes it. Right? Because this right-hand endpoint over here, this 1 over alpha, is creeping closer and closer to 0, and it eventually becomes 0. If we take the limit, right? If we take the limit as alpha goes to infinity, 1 over alpha will be approaching 0. So that means that nothing to the right of 0 is going to survive this intersection of all of these sets. Right. Okay, what do you think? Any questions on that? Does that make sense? So this is just, I'm showing you this notation, just arbitrary unions and intersections. It's something that's pretty common in math to try to make as much of a general theory as possible. Sometimes we can do arbitrary unions and intersections. Let's do an example. One last thing with set theory, and then we'll either start into functions today or we'll just hit that on Thursday. I want to do one more proof-oriented example involving these arbitrary unions and intersections, because there will be some of this in the homework, and I find sometimes that people have trouble with this, mostly just because of the notation. It's not that they don't understand the problem, it's just the notation. So let's do this. I'm just going to, for this example, I'm going to let script A be equal to the set of A sub alpha, where alpha is an element of I. And I'm going to let that be an indexed collection of sets. And let capital B be a set. So I'm going to take some other set, capital B. All right, so there's a whole indexed family of sets, and then there's some other set B. And what I would like to prove here, guys, what I would like to try to have us prove is that if we take the intersection of the A sub alphas, where alpha is an element of I, and then take the union of that with B. Okay, so make sure you add some parentheses on this. So we have the intersection of the entire family of sets in parentheses, and I'm going to take the union of that with B. My claim is that that's the same as if I do the intersection, where alpha is an element of I underneath of that notation, of the quantity A sub alpha union B. There we go. So I think I've written it down correctly. I got a little bit tight on space there, but I think I've got it correct. Let you guys catch up while I erase here for a second. I would like to try to prove this. And we talked earlier about proving set equality. Get myself the whole board. We're gonna need a little bit of room to write this one up, so give yourself some space for this one. We talked a little bit ago about proving that two sets are equal, and I know this is just abstract and it may feel a little bit dry. I promise calculus does get more interesting than this. Okay, but we have to get warmed up a little bit for the semester. So to prove the equality of sets here, you remember I mentioned it earlier that I like to prove it in two parts. The left side is a subset of the right side, and then conversely, the right side is a subset of the left side. So I go both directions. Let's start with the left side being a subset of the right side. I'm going to start off by just saying let X be an element of the quantity of the intersection of the A sub alphas union with B. Okay? So now we're really going to get some practice with our proof writing. Because, well, this means that X is an element of the intersection of all of these alpha i's of the A sub alphas, or X is an element of B. Remember, union just means or. So I have these two scenarios. Now guys, whenever you are in the midst of proving something or something. Or, sorry, not proving it. Whenever you are assuming one thing or another thing, then you actually need to essentially do a proof by cases. You need to do one case where we say, well, maybe X is in this intersection, right? And then we need to do a second case where, well, maybe X is in B. So I'm gonna set that up right now. I'm gonna set this up using cases. Case one is going to be assume. This is not necessarily true. We are going to assume this as one of the possible cases. So I'm going to assume that X is an element of the intersection of all of those A sub alphas. This is case one. Later on, I'm gonna have case two, where I will assume that X is an element of B. Okay, but for now, I'm going to assume this. At some point, we should probably stop and just make sure it's clear to us what we are trying to prove. You know, I sometimes get on an autopilot train of thought where I just sort of start with my assumption, I just write everything down that I can get out of it. But at some point you need to go back and say, well, what is it that we're trying to get as our conclusion? This is what we're trying to aim for, is that X lives in this intersection, right? In other words, X needs to live in all of these sets for every alpha. And so the way to set that up is to say, well, if I have to prove something for every alpha, which is what the intersection requires, then I should pick an arbitrary alpha from capital I and prove that X lives in that set that goes with that arbitrary alpha. I'm reviewing proof writing 101. I should say proof writing 280. Right, is really what this is about. To prove that X belongs to all of these sets, I am going to fix some alpha naught in capital I. You don't have to call it alpha naught if you don't want to, but I like to sort of imagine that I'm fixing that alpha naught. It's one of the sets in my, it's one of the elements of my index set, capital I. So I'm going to fix that alpha naught. And the first thing I'm going to point out is that we're going to note right away that X does live in A sub alpha naught. That's because X actually lives in all of the A sub alphas. It's in the intersection, right? We are assuming this. We are assuming that X lives in this intersection. So X must live in A sub alpha naught. But guess what, guys? If it lives in A sub alpha naught, then X lives in the union of that with anything. So X would live in the union of A sub alpha naught with B. Because remember, to live in the union, I only have to live in one of the two sets. Okay, so X lives in that union, and that was for an arbitrary alpha naught. Any element of capital I would have had us reaching the same conclusion. And that means that X does live in this intersection. Do you see that? It's because the alpha naught is arbitrary. We have not dictated specifically which set this alpha naught refers to. It could be any of them, which means that X lives in all of those, right? So hence, we're going to just finish this right here, guys. I know I don't have a lot of room, but I'm going to make it work. X is an element of the intersection. I'm hoping this is readable. Alpha is an element of I of the quantity A sub alpha intersected with B. I'm sorry, union with B. That's a union with B. There we go. And I'm going to put a little check mark there because that's the end of that case. Is that readable? I hope it's readable. So it just said, basically it just says, hence X is an element of this set here on the right, which I think is a little bit bigger print up here at the top. Okay, that's case one. But I have another case, and I'm going to do that one over here, case two. Case two is going to be to assume the other possibility is that X was an element of B. Right. So I have to do both cases because I don't know for sure which of the sets X belongs to. It might belong to this intersection of the A sub alphas, or it might belong to B. If X belongs to B, we still have to do the proof, right? But the good news is that if X belongs to B, then X will belong to A sub alpha union B for all alpha in capital I. And I really want to, I've kind of already mentioned this earlier, but just to really reiterate it again, the precision of the wording and the necessity of the wording is really high in Math 350, almost as much as any class you're going to take in this major. If you don't write the words for all alpha in I, somebody might think you're talking about only one alpha in I, or for some alpha, or for any alpha. So it's really important to add those qualifiers there. If you like using this upside down A, instead, that's a kind of a shorthand notation for all, that's okay in this class. I will accept those kind of logic symbols, but there needs to be a symbol there. That's kind of what I'm trying to get at. Okay, so, but if X lives in all of those A sub alpha union B's, thus, that's what it means for X to be an element of the intersection of A sub alpha union B over alpha and element of I. So we're doing a nice little proof here using the arbitrary unions and intersections that we were just talking about. That's what we wanted to get, and I'm gonna put a little check mark on that as well. All right. Looks good to me. So far, so good. Any questions on this first half of the proof, guys?
I have a question for case one.
Yeah.
When we're saying that alpha or alpha naught is in I, isn't that just for one alpha naught?
It is for just one alpha naught, but the alpha naught is arbitrary. It is not being prescribed to be specifically a particular, I mean, it is being picked to be one specific alpha naught, but we don't know which alpha naught it is. We don't know which element of capital I it is, which means that whatever we say after that moment can be true or can be applied to any of the alphas in capital I. And so we can make this sweeping statement for all alpha in capital I. We're only fixing one of them, but we're making a statement that applies to any arbitrary one of them, right? So if I say that, if I want to prove that, you'll get a parking ticket in any of the 50 states for parking in front of a fire hydrant, right? And I want to prove that statement, I have to sort of pick a fixed but arbitrary state. So I'm going to imagine that one of the states is fixed, and I'm going to say, look, the laws dictate that you will get a ticket if you park in front of a fire hydrant, right? That argument, that basic argument, would transfer to any of the 50 states in the same way. So I don't have to do 50 different proofs. I just make that basic argument with one arbitrary case of it. That's kind of what we're doing here.
Okay.
Sweet. Good question. Good question. All right, guys, let's try to prove the reverse direction. We've only got a few minutes left, but I think we have enough time to go the other way with this. This is a nice example, I think. On Thursday, we'll probably do a little group work, and I'll have you guys practice another one kind of like this. But let's try to prove the reverse direction. So that would mean that to go the other way, I'm going to let X be an element of the intersection over all alpha and element of I of the quantity A sub alpha union B. So let's assume that X lives on the right side now, and I want to prove that X lives on the left side. Now here's the thing. We are trying to prove this thing now, right? Okay, I need everybody to listen closely on this. This comes up, I mean, I know you did it in 280, but it's a logic point that is really important. If you're trying to prove a union, if you're trying to prove that X lives in a union, let it be clear that you will not be able to prove specifically which of the two sets in the union it belongs to. If you try to do that, it will not work, because if it was possible to prove that X specifically lives here, they would have just asked you to prove that. Or if it specifically lives here, they would have just asked you to prove that. But no, they're saying, we don't know where it is, but this X is here or here. Whenever you are trying to prove an or, right, which is what we have here, we would like to prove, so I'm actually gonna write it down this time. We need to show that X lives in the intersection over the alphas and I of A sub alpha, or that X lives in B. We need to prove that, because this is a union right here on the left side of what we're proving. So I am trying to prove that X lives in this box. And that means it needs to live here or here. We don't know which one, and we're not going to know which one. But whenever you are trying to prove an or, okay, let this be heard. Whenever you are trying to prove an or, the best way to do it is to assume that one of them is not true, and thereby forces the other one to be true. So to do this, assume that X is not in B. Let's assume that X is not in B. Now, if you prefer to assume that X is not in the intersection, that would also be fine. I think it's a little cleaner in this particular case to just say, let's assume that X is not in B. I mean, if X is in B, then we would have already won, right? We're trying to prove that X lives here or here. If X lives in B, we're already good to go with our proof. So let's assume that things are not so nice and that X is not in B. And I'm going to now try to convince you, hopefully, that X must be in this intersection. Now, here's the thing, guys. If X does not live in B, then it does live in this intersection, right? So from the assumption, X is an element of A sub alpha intersect B for all, here's that important language again, for all alpha in capital I. From the assumption X lives in all of those sets. But we're saying that, oh, you know what? I wrote that wrong, didn't I? Did I write that wrong? I did. Every so often, I'm gonna make a little mistake just on purpose, just to see if anybody's paying attention to me out there. So, just kidding. I just made a quick little typo here. This should have been a union. This should have been a union right there. It says union, right? That's a union. Right, A sub alpha union B. So from the assumption, X lives in A sub alpha union B. It lives in this one or that one. But since X does not live in B, what are you going to conclude? It's not in B, but it is in the union of A sub alpha with B. So then X must be an element, right, of the A sub alpha. And this is for all alpha in capital I. This is for all alpha in capital I. Oh, well, that's exactly what we wanted, right? So thus, X lives in the intersection of all of the A sub alphas. And that is what we wanted to show, right? If X did not live in B, then we wanted to show that it would be forced to live in the intersection of all of the A sub alphas. Does that make a little bit of sense? Guys, do you notice how different the two halves of the proof are? You have this union on the left side that's in this box here. And when we assume that union, we end up having to do cases, 2 cases, right, to prove that. When we want to prove the union, That's where I'm saying, well, what you should do is negate one of the possible outcomes and then try to prove that that forces the other one to be true. This is so important in a class like 350 is whether you're assuming something or whether you're proving it. Because the sort of the direction of the proof makes a difference. Try not to fall into the trap of, oh, I'm just going to write the proof in one direction and then I'm just going to reverse it. I'm just going to like turn the whole thing around to do it the other way. Sometimes proofs will work that way, but not often. Not that often in this class. You almost have to take each one of these things and view it as like two problems that have to be individually solved. Okay? But this was a nice example to kind of combine the set operation stuff that we did earlier with the arbitrary unions and intersections that we've discussed here in the second half of our class today. Are there any questions about it here? Okay, well, I have hit 250 on the dot. I think on Thursday, I'm going to jump right into section 1.3 on functions. Most of your assignment for Friday, you should be able to get a jump into it. Maybe not the very last problem that's from section 1.3, but see if you can get started on the homework. I am going to have some office hours later today, as well as Thursday and also on Friday. If you need any help with any of the homework, you can always come talk to me. But I think if there's no other questions, I am going to kind of let us sign off for now. I'm going to get this copy of today's lecture into Canvas for you also by tonight. So are there any questions before we go? Okay, well, it's nice to meet you guys. I'm looking forward to seeing you in person in a couple of weeks, but thank you for being here in Zoom today. And I'll see you right back here again on Thursday, same time, same station. All right, bye for now.
Bye, Dr.
All right,
Annan.
thank you.
Bye,
Good to see you guys.
Dr. Annan, I
Yeah.
emailed you about the book because my book isn't getting here till the 23rd.
Oh, okay.
there-
So would you like me to send you some pages to get started?
Yeah, at least just like the homework problems would be great.
Okay, let me do that in the next few hours today when I get a chance, okay?
Awesome. Thank you.
And I'll do it through Canvas.
Okay, perfect.
Sounds good. Okay, great.
Thank you.
Professor, I shot you an email about possibly trying to audit your class if you have time to respond to that.
Sorry, one second. I'm just trying to figure out where my thing is. I was gonna try to stop recording this thing. That's the main thing I want to do right now. One second. Sorry, one second. I just.
Fine.
No, that's not the one. Okay, if I go like that, and now I pull this up, no, it's not. Oh, maybe I need to be. Hey, John,
Yes, Professor.
why don't you meet me over in my Zoom office? I'm having a little technical difficulties. I'd like to end this session so I don't record this whole conversation into my Zoom. Could you come over to my Zoom office in like 2 minutes?
I would like to. I don't know how to get there.
Oh,
I did email you. If you just want to respond to that, I can pop in a link through that.
I thought I didn't see your email. I'm gonna put it in the chat right now. Can you see that?
My chat. Thank you.
Okay, why don't you just come over there? I'll be there in 2 minutes. Arusha, same thing. I'm gonna log off for now. Okay, come on over to
Let
this
me
number
just-
512-459-2043. I'll see you guys there, and I'll just be there in 2 minutes.
Okay, awesome.